discuss the Hamiltonian formulation for the solution of optimal control problem, and then we will consider some numerical example. So, this is formulation is Hamiltonian formulation for solution of optimal control problem, of course, using calculus of variation. So, if we recollect why we are going for a Hamiltonian formulation, suppose the system dynamics or system plant is described in state space form, means any system can be described with a n dimensional vector. Agree? So, n dimensional what is called any system can be described with a n differential equation, n first order differential equation. If we represent the system in state space form, it is convenient to deal with Hamiltonian function rather than the Lagrangian function. So, let us recall our earlier problem. Consider the plant or system x dot is equal to f of x t, u of t and t, and this dimension is n cross 1, this is n cross 1, and this state number of states is n cross 1 and number of inputs to the plant is m cross 1. You can think of it, we have a plant or system, this one input is u of t whose dimension is m cross 1, and the state you can say output is the state, you can say x of t whose dimension is n cross 1. So, this plant is described in general we have a dynamic system is there, we can describe with a nth order differential equation, which can be converted into a what is called n first order differential equation. So, once you convert into a state space form, then our problem is here, and the corresponding performing index j, if we recollect this one, we have written x of the terminal cost is a function of x t and t at t is equal to t f final time plus integration of t 0 to t f v x of t, u of t and t dt. So, our problem is to find out the control law u such that this performance index is minimized. Not only that, subject to the constraint that equation, let us call this is the equation number 1, that is the equation number 2. So, our problem is to find out the control law u of t, which in turn to find out the optimal trajectory x of t such that this performance index is minimized subject to this constraint equation number 1. That is what we discuss last class, and correspondingly we got what is called the necessary condition. If you say our necessary condition along with the boundary condition, we got it that del L this x of t minus d of dt del L dot function of L is a Lagrangian function, which is a function of x t, u t, lambda t and comma t. So, that differentiate with respect to x dot of the whole, that you solve this one along the, because you have to find out star means you have to solve this one, whatever the solution you will get it, that is the optimal trajectory or optimal control law, from which in turn it will give you the optimal trajectory x star of t. So, that equation you have to solve. So, we have a in turn we have a n cross 1 differential equation is there. So, that differential equation in general it is a nonlinear differential equation. So, that is let us call equation number 3, and not only this another x condition we got del u del t, this one is equal to 0. So, this is equation number 4 corresponding to our this problem, and we have a boundary condition. That boundary condition, if you see this one, that we obtain boundary condition, we obtain L Lagrangian function minus del L of with respect to x of t, that since x is a vector. So, L is a scalar quantity, that will be a vector, column vector. So, we have to take transpose of that one and then multiplied by x dot of t. So, this you along the trajectory extra, then t is equal to T f. This is the boundary condition, we got it when T f plus then del L dot del x dot of t whole star t is equal to T f and delta x f is equal to 0. So, let us call this equation is 5. So, and we know what is the L. The L expression we have written in terms of what is called Hamiltonian functions, where L dot, which is a function of x t, comma u t, comma lambda t, comma t. So, this is a function of that Lagrangian function is split up into a what is called Hamiltonian function and then Hamiltonian function free form x dot, agree. So, this is the Hamiltonian function and that function is called Hamiltonian function. So, Lagrangian function, this Hamiltonian function is nothing but a, if you see what we have considered this, the that we will write it in this plus del s dot plus del x of t whole transpose x dot of t plus del s of t del t minus lambda star sorry lambda transpose of t x dot of t, agree. So, this this is a function of what is called v. V is the that function, if you see integrand part of this integral one, v plus Hamiltonian function plus lambda transpose of f, that one. That means, these two terms, if you see this term and this term is free form x dot, and that function we consider as a Hamiltonian function. Because why you have expressed that necessary condition, what we got it here, necessary condition equation number 3, 4 and boundary condition 5. If we express this thing into Hamiltonian function, then we will see if the system is described in a state space form. If we express this in place of Lagrangian function, if you replace by a what is called Hamiltonian function, a set of equation, what will get it in a simpler form, and it will be easier to solve what is called if the description is state space form. So, that we will see later of this one. So, this is our equation number, let us call 6. Now, we replacing the, you can say using 6 in 4 to using 6 in equation 3, that is the 3 equation, not 4, 3, 4 and 5, 3 to 5 comma we get what, let us see. So, our first form 3, we can write form 3 is del 3, you see del L del x. So, in place of del L, I will just write it in terms of h, that whole expression I will write it. So, del L del x, in place of L I am writing h x of t, u of t, lambda of t, comma t, this one, plus delta S dot of that x of t whole transpose that dot of t plus del S this del t minus lambda transpose of t x dot of t. So, this whole thing, if you just say the whole thing from here and including this one is nothing but our L Lagrangian function. So, I have just written the first term of our equation, this is that one. Then second term, if you see this one, I am writing is minus d of dt, then del L again this whole quantity, differentiate this with respect to x dot. So, what is the del L? I am just writing h x of t u of t lambda of t comma this plus del S dot del x of t whole transpose x dot of t plus del S dot del t this one minus lambda transpose of t into x dot of t. So, that is our we have written L, this whole thing just same as this one, same as this one we have written it here. Then this is differentiating with respect to x dot. Now, look at this expression that one chain rule we have used frequently, that chain rule is like this way. Suppose we have a function x is a function of x t, t is the parameter and y t and z of t, this is the function of this. Now, if you want to find out the differentiation of x with respect to dt, this is nothing but a partial differentiation of f with respect to x then x dot, then del f del y, then another variable del y of t, then y dot plus del f del z of t is equal to z dot. So, what is this? If you have a function x of t, y of t, function of x, y, t, which is a function of time each, then I can write differentiation of x with respect to time t is nothing but a partial differentiation of x, partial differentiation of f with respect to x multiplied by x dot of t. Similarly, partial differentiation of f with respect to y t is y dot of t and z dot of t. So, these things we will write it here. Now, see this one, S is a function of what? This and this I can write it. S is a function of x t and t. This is a function of, if you see, this is the function of x t and t, this one. So, now I am writing it this one that this and this term and this term combinedly I can write it. Look, this term by using the chain rule, this term and this term combinedly I can write it that del d s of d t, that is what we can write it. This and this combinedly I can write. So, rewrite this equation, what we write it, this one, just say del L del x of t, then h, I am not writing h dot, means it is a function of x t, u t, lambda t and t, this h plus d s dot d t, agree, and what is left, this and this d s or d t and lambda transpose minus lambda transpose of the x dot of t, agree. This is the first part we have simplified. Then second part of the Lagrange equation d of dt, see this one, that whole thing this is this quantity you are differentiating with respect to x dot. H, this h is not a function of x dot. So, if you partial differentiation, if you do with respect to x dot, this term will not be there. Okay? The first term will vanish. Then this, and this is a function of s is a function of x t and t. So, this is a function of x dot. So, we can take this is a constant because it is not a function of x dot t. So, if you do the differentiation of this one, del s, this del x, del s partial differential of s with respect to x t, we will get it that one. Agree? And this is not a function of x t, x dot t. So, this will not come into the picture. So, and now it is a function of x t. So, only this term and this term will be remain in the differentiation of the Lagrangian function with respect to x dot, when Lagrangian function expressed in Hamiltonian form. So, this term ultimately it will come, if you see, is coming like this way. If you just do it, then it will come, and if you recollect once again that if you have a function, if you are differentiating that function with respect to x, x is a vector, let us call say, and you are getting A transpose x, A is a row vector, A is a row vector of dimension n cross, this is the row vector of dimension 1 cross n, and this is n cross 1. So, it is a scalar quantity. So, that is differentiating with respect to a vector, that results is A. So, now if you just use that one, the differentiation of this is, you can consider is a scalar multiplied by a what is called differentiation this thing by a what is called a vector. So, that results will be a row vector, and you are differentiating with respect to this. So, results will come del the differentiation of this with respect to x dot, that term. So, I will ultimately I will get differentiation of s with respect to x of t and this term. Similarly, this is minus lambda transpose x dot, differentiation x dot is equal 1, and this will be lambda of t minus lambda of t. Okay. So, this whole thing, if you see this one, you can put it, that whole thing is in bracket of that, you if you just do it here, this is not L, this is of that one is star, you can put it, if you like you can put it in star, that one. Now, this equal to 0, because what from where you are getting that first equation of from equation 3, this equal to. So, right hand side of this one equal to 0, this one. So, from 3 I am writing, from 3 this is 0, and I am getting that one. Now, see, look at this expression, differentiation of partial differentiation of that quantity with respect to x of t, and this order of differentiation we can change it. So, if you change it, this one, this is plus, this is minus. So, this is cancelled. Okay. Only is left over is this one del h del, because that is the function of you have to differentiate with respect to x t. So, that will be vanish, that there is this is lambda t, lambda transpose t x dot of t. So, you have to differentiate with respect to x. Ultimately, it is a del h, this del del x of t whole star, agree, this bracket, this star is here, this, and this is also star from here to here. So, this equal to this plus, this is minus, this is minus plus, equal to your this term is what, differentiation with respect to t, that. So, it will be coming minus minus plus, if you take right hand side it will be lambda dot of t. So, let us call this equation, we have used the equation number up to 6, let us call this is equation number 7. So, now see this one, when you use the Lagrangian equation, the del L del L Lagrangian function you partial differential with respect to x minus d of dt del L del x dot is equal to 0. So, this expression is boils down to what is called a simple Hamiltonian function form. This is, and this function is free from x dot, is a function of x, u t, lambda t and t. So, next is, so this is the this equation, and what is this equation? Another equation is that one. From 4 what we can write? From 4. So, your h is L is expressed, if you see L is del L del u, if you do del L del u and L you express that one. So, it is a function of you are differentiating partial differential with respect to u, there is no u is here. So, del h del u must be 0. So, from 4 we can write del h dot del u of t whole star is equal to 0. Let us call this is equation number 8. Again, now you see this one, another expression we call this equation is called what is called co-state. The equation number 7 is called co-state equation. Co-state equation. Agree? So, this is the co-state equation. So, another equation one can derive like this way, del h dot del lambda, del h del lambda is equal to x dot of t. Now, see our objective function, if you see, if you refer to your last class note, if you see, we have written the what is the Lagrangian function, we have written the objective function plus the lambda transpose constant, that is our Lagrangian function. So, del L del one of the what is called KKT condition, del L del lambda must be equal to 0. So, we can get this equation from Lagrange expression, one can get this expression from Lagrange function or expression. So, this is also, if you like, you can write star this one. So, let us call this equation is equation number, this is the equation number 9. So, this called is optimal state equation, and you see the co-state equation dimension, because lambda dimension is, if you say n cross 1, same dimension of the state vector. So, that is why it is called co-state equation. This equation and this equation, nature of this equation and this equation is there are co-state one of co-state of another. So, this is called co-state of a state equation vector. So, now we have that this is the equation number 3 is now when you express Lagrangian function in place in terms of Hamiltonian matrix, this expression simplified form you are getting del h, that corresponding expression, that one will get in simpler form del h del x equal to minus lambda dot of t. Another expression you have try in place of del L del u, partial differential Lagrangian function with respect to u, when L is expressed in terms of what is called that Hamiltonian matrix, then we will get del h del u, and the state equation, that what we have equation is del h del lambda is equal to x dot of t. So, now see the boundary conditions. If you see the boundary condition of that one, then what we are getting it, we will just see the boundary condition now. So, note, and the boundary condition what we will do, we will replace the Lagrangian function in terms of Hamiltonian function, that is all. What is the final boundary condition we will get, that we will see it. So, the boundary condition and our original problem, a boundary condition is expression is equation 5. So, boundary condition 5 is now replaced by in the form of boundary in the form of Hamiltonian function. So, boundary condition is now replace Lagrangian function in the form of, now you replace Lagrangian function in the boundary conditions, Lagrangian function in the boundary condition in the form of Hamiltonian function. Now, replace the Lagrangian function in the form of Hamiltonian function. If you replace this one, now you see first what we will write it for this one, L, that equation number 4 if you see here. So, this is H, you will get it, that is L differentiate of this with respect to x whole transpose x dot, putting t is equal to T f, that one, and then del L del x dot t is equal to f del x T f. So, let us see what we can write for this one. So, we can write it for this one, if I just put it here, that let us call rewrite 5, equation 5. If I rewrite this one, L dot minus L dot of this x dot of t whole transpose x dot of t, agree, then this trans star t is equal to T f delta T f plus delta L dot del x dot, agree. Del x dot whole transpose, then your star t is equal to T f delta T f. Now, see this one, our expression for that one, what we can write it. L is a, what you can write it, this L is our expression, Lagrangian function expression H plus. So, if you write it this one, you just see what we are writing, L is nothing but a H dot del S del x of t whole transpose x dot of t, agree, plus del S of t del t, this, agree, minus lambda transpose, this is lambda transpose of t x dot of t. So, this I have written in place of L. Now, this L is a, see that one, L is now we are differentiate with respect to x. So, if you do this one, then what we will get it, this when we are differentiating with respect to x dot, then it will be a del x, this we are whole thing we are differentiating with x dot, then it will be a, if you do differentiate with respect to x dot L, here is x, this. So, minus, see this one, I am differentiating this with respect to x dot. So, you have a minus minus x is. So, this will be del s del x whole minus there is a x dot here. This is L. I am differentiating this thing with respect to x dot. So, then what will be this one? This will be a del s del x t minus lambda t, agree, minus lambda t of that one, and this is the bracket, that thing will be bracket because it is a minus sign is here. So, the whole thing is a bracket, agree. So, I have written, if you just take this one L del x dot transpose x dot, what is this value, that I have written it, that quantity, agree. Then this star T is equal to T f delta T f plus again this term, this equal to 0 because our boundary conditions from 5, this is equal to 0. So, next I am writing similarly, that one will be delta s delta x of t, there is differentiation with respect to x dot. If we are differentiating with respect to x dot, that is x delta of x t, this minus delta of t plus term, and that you are making star t is equal to T f and delta x f is equal to 0. So, now see what is it, this is L and this is the delta L, you are doing the differentiation of that one with respect to x dot, agree, we got it that one. Then again it is a differentiation of this with x dot, we will get it this one. Now, see this one, what simplification we can do it here, because now delta s, and there I missed it here, that your what is called x dot, you see this expression, that this is the x dot is there, that x dot is missed here. So, delta s, this is transpose also, this delta x dot, this x dot, this cancel. Now, this is plus, this is minus. So, this term cancelled, this term cancelled, what is left, that is h plus delta s dot, this is dot delta t, this term whole star t is equal to T f delta T f plus what is left here, delta s dot and delta x of t minus lambda of t, this is a transpose, that lambda transpose this, that is star t is equal to T f and L delta x f is equal to 0, agree. So, that, and this is our boundary equation is this. Now, see what I did it, I just replace once again, I just what I did it, this is the necessary condition when expressed in Lagrangian function, and when Lagrangian function is expressed with a what is called Hamiltonian function and some other terms, we replace it L by this and do simplification, we got that expressive condition del h del lambda is equal to x dot, that is what we got it, agree. Then this expression when you replace by Hamiltonian function L expression, then we will go, we got it del h del u is equal to 0. Similarly, the boundary condition what we did it here, when we just replace that expression boundary condition with in terms of Hamiltonian, we got it this function, that is x dot, okay, this expression. So, our simplified form, not this expression, that is just now we have calculated this expression in terms of Hamiltonian. So, this is the important boundary condition in terms of Hamiltonian functions. So, now we will summarize this point. So, if you see this one, this is the basic three equation we need to solve now. This is the equation 7, 8, del h del x is equal to minus lambda dot t, when the system dynamics is expressed in terms of what is called state space form, and then we can solve this one by using the Hamiltonian function, where the Lagrangian function is expressed in Hamiltonian function form. If we express in that form, then del h del x star is equal to x dot, what is called x dot lambda dot of t, that one expression. Then del h del u is star is equal to 0, then another expression. So, this dimension is m cross 1, this dimension is n cross 1. Okay. The next equation, what we got it here, that equation 4, 5, page number 5. So, this is another equation we got it, the del h del lambda is equal to x dot of the, so is the state equation of this, that one can get it from Lagrangian equation of this one. Then this is the boundary condition. So, this is the equation number 9, this is the equation number 10, let us call. So, if you solve the equation 7 to 10, then you will get the trajectory of control input, as well as which in turn it will give you the trajectory of the state trajectory path in optimal path of this one, which will minimize the our objective function or performing index. So, we will summarize the results like this way. So, if you see this our problem algorithmic steps now, algorithmic steps. So, if you see our problem is like this way, given the function, our problem is x dot is equal to plant is given a x, okay, plant is given x of t, u of t and t, and performing index is j, the terminal cost is x of f t f t, or you this, or you can write it x t comma t, t f is equal to t is equal to t f, this plus t 0 to t f v x of t u of t this dt. So, what you form it? You form, first step is form the Hamiltonian matrix x of t, u of t, lambda of t and t. What is the Hamiltonian matrix? This integrand plus lambda transpose of t into f of x of t, u of t and t, and this dimension n cross 1, and the whole dimension is 1 cross n, 1 cross n. Okay, so, this is the scalar coordinate. So, this is free form x dot, this Hamiltonian function. Once you know the Hamiltonian function, then our what is called step is there, step 1, compute del h del u is assigned to 0. Let us call this is equation number. Once I know the Hamiltonian function from the performing index given and the constraint, this is the constraint. Our problem is finally we have to find out u of u t or u star of t such that this performing index is minimized subject to the constant equality constant, and that equality constant may be linear, may be nonlinear dynamic equations. So, this is the first equation. Second equation, the state equation that we have written it del H dot del lambda of t. This, if you like, you can put it, because you have to solve it, and what is the solution you give, that is the optimal, star means optimal solution you get, or you can omit this star, it does not matter, because you have to solve this equation. So, that equal to this equal to x dot of t, agree. So, this is also n cross 1, let us call this is equation number 2, and this is the called state equation. Then third is lambda del h del lambda del h del x partial differential h with respect to, that means what is called Hamiltonian function you differentiate with respect to x, which is equal to minus lambda dot star, lambda dot star, this is if we give star, that one, and this is the your co-state vector. See this one, what we got it from this, from the Lagrangian co-state vector, that expression is the third. So, this is the equation number 3, and then you have to solve these 3 equation by using what is called boundary condition, that our boundary condition is del h Hamiltonian function del s, which is a function of x t and t, del t whole star t is equal to T f delta T f plus del s dot del x dot of t, x of t, this minus lambda of t whole star t is equal to T f into delta x f is equal to 0. Agree? So, this is a vector, agree, Columbar. So, transpose is there, that. So, this transpose, do not forget to give transpose, that one. So, this is the boundary condition, and this is the boundary condition in terms of Hamiltonian function boundary condition. So, if we just recall once again that given the plant dynamics, this x dot is equal to f of x, or performance index is that way, this is the terminal cost and this is the integrand part of what is called cost function. Then our first step is find out the Hamiltonian function. That Hamiltonian function is nothing but a integrand part of this integral, this one plus the Lagrangian multiply into f of x. That is, you have seen it, how we have converted a constant optimization problem into unconstant optimization problem using what is called Lagrange multiplier technique. So, this is that Hamiltonian function. Once you find out the Hamiltonian function, then differentiate that partial differential of h with respect to u, because h is a function of x t, u t and lambda t and t. So, next is once you find out, then differentiate that h with respect to lambda t, that will be a x dot of t, agree, that we have derived this one. Next is, if differentiate this with respect to x t, partial differentiation of s with respect to x t, that will be given lambda dot of t. So, this will be giving you the what is called boundary condition of this one, that. So, and this is the 4 equation you have to solve simultaneously. So, next question is, let us call, we take a simple example, and okay, before that, what is that after solving this one, what is the guarantee that objective function or the what is called your that performance index will give you the minimum value of the functional or maximum value of the functional. So, that is called sufficiency condition, sufficient condition, sufficient condition. So, that sufficient condition, if you see this one is provides to determine, it provides, or in order to determine the nature of optimization. Either functional value is minimum or maximum, this is the nature. We must confirm this one. That can be done by using sufficient condition. We have already derived what is the sufficient condition is there in terms of Lagrangian function, and if you replace that L in terms of H and some other terms we have shown it, if you replace L by Hamiltonian function plus some other terms, then you will get it the second variation of the functional, this equal to T 0 to T f delta x of t transpose then delta square h of this delta x square capital X. Let us call it right capital, because we have started with the capital X vector, this one, this star and delta x of t plus twice delta x of t whole transpose then delta square h delta x of t then delta u of t multiplied by delta that whole thing compute at along the trajectory, optimal trajectory, del u of t, agree, del u of t, agree, then plus del u of t whole transpose del square L dot del u square of t, agree, whole this del u of t, that whole bracket, and that you differentiate with respect to dt. So, we know this one, the delta square of this must be positive if the functional value is minimum. If that value will be negative, delta square will be negative if functional value is this integration value is negative. If the integration value is negative, then function value is maximum. So, this you can write it, one can write this thing into a matrix and vector form, T 0 T f del x t, and this is what this matrices, this is a Hessian matrix, symmetric matrix, agree, this is the symmetric matrix, you will get it. So, that we can write it now del u of t transpose, this whole thing is a scalar quantity, that we can write it in quadratic form. So, you are writing del h square dot del x square of t del second derivative of h with respect to del x del u. The order can be changed, del u del x, this does not matter, the results are same. So, del x del u of t, then del square h del u square of t, that whole thing at along the optimal trajectory u t x star multiplied by delta x t and delta u of t, this, and then differentiating with respect to this. So, delta square, the second variation of functional, second variation of the functional, if it is a negative, that second variation is a scalar quantity. If it is a negative, indicates that this integrand part, that matrix whose dimension is, this matrix dimension is n plus m into n plus m matrix dimension, and that is a symmetric matrix, and that matrix must be a, if it is greater than 0, that matrix must be a greater than 0, means positive definite. If it is a positive definite matrix, then we will call that our what is called functional value is minimum, and at what point along the trajectory u star and x star, and that u star solution and x star which will got once you find out u star, x star also you can find out, and that is the optimal trajectory that we obtain by solving equation. Just now we have mentioned it, by solving equation, that algorithmic steps, if you see it, by solving the equation, that our, that is, just a minute. That means, our equation is del h del u, that means, that 3 equation you have to solve it. Del h del u is equal to 0, that means, if you write del h del u is equal to 0, then del h del lambda is equal to x dot of t, that you have to solve it, and del h del x is equal to, again this one is equal to lambda minus lambda dot star, agree, this your lambda dot star, the star you can write it, these 3 equation along with the that boundary condition, that just now we have written the boundary condition and this boundary condition. Okay, 4 equation number, that means equation number 1, equation number 1 del h del u, equation number 2 del h del lambda a x dot, and equation number 3 del h del x is equal to minus lambda x dot, and equation number 4 is necessary to solve the a set of nonlinear equation, that boundary condition is required. Okay. So, that way we can solve it, this one, and once you solve the optimal trajectory, in order to check whether the functional is a optimum, means minimum or maximum, to show this one nature of the optimization, that this matrix, that is this matrix I am now writing, this matrix, the Hessian matrix del h del dot del x square of t del h dot del x of t del u of t del square h dot del x of t del u of t del square h del x del u square of t, agree. So, this matrix, if it is greater than 0 means positive definite matrix, agree, and this matrix is a symmetric matrix, this matrix is symmetric matrix. If it is greater than 0, it implies that functional value is minimum, that j star is minimum, functional value is minimum. If it is less than equal to 0, the negative definite, this matrix is negative definite along the trajectory, optimal trajectory, what we got by solving just now mentioned equation number 1, 2, 3 and boundary condition, that one. if you and put it here in this matrix, if you get a negative definite, this implies that J star is maximum, function value is maximum. So, this is the necessary and sufficient condition. You have to, necessary condition is required to find the trajectory of the what is called trajectory of control u of t and x of t. Once you get it optimal trajectory of u star of t control in effort u star of t and x star of t optimal trajectory of the state variables, then next question is to know the nature of this optimality, whether it is a objective, whether the objective function or functional value is minimum or maximum, then you have to test with this matrix, and that matrix dimension you see n is the number of states, m is the number of inputs. So, it is n plus m into n plus m, that matrix you have to check it. If it is a positive definite, J star is minimum, if it is a negative definite, J star is maximum. So, this is the basic theorem of this one. So, we will take an example and see that how to solve a problem, a practical problem of this one. Agree? And you can see this one, we can just consider the three cases as a case A. Similarly, as we discussed earlier, fixed time, fixed final time and fixed final state. This is the case 1. Then case 2, we can see the fixed final time, and you see that case B, free final time and fixed final state. Similarly, case C, we can say the case C is the fixed final time, fixed final time and free final state, and last one case D, both are free, case D, but free final time and free final state. So, this whatever the we have considered the boundary condition, all these thing, that is one of these cases will be a special case of that general boundary condition. So, we will stop it here. Next class we will just take an example and show how to solve this problem by using the Hamiltonian function method to get the optimal value of the functionals to solve the control problems. Agree? So, we will stop it here.